Hello everyone, today we'll be solving problem 7 from homework number 7. So this is a phasor problem, and so with any phasor problem, the first thing you want to check for is the frequencies of the independent sources, the independent AC sources. So as we can see over here, these are the two equations for the independent sources, this for this source and this one for the current source. So as you can see right here, that the two values are not equal. This means we must use superposition. So, however, there's one important thing to notice that with this circuit is that we have a DC source over here. So this means that even if these two values were equal, we'd still need to use superposition because a DC source can technically be thought of as having a frequency of 0. So, another important thing with phasor problems is that you want to make sure that these two equations are in the same form, meaning that they're either both cosine or they're both sine. So here they're both cosine, so we don't have to worry about that. So with superposition, you have to choose which source you want to isolate first. So I've gone ahead and chosen the DC source, and I've redrawn the circuit right here. So when isolating a source, that involves turning off the other sources. And so turning off a current source creates an open circuit, as you can see right here, and turning off a voltage source creates a short circuit, as you can see here. Now, important to note is that this capacitor is also shorted, so we can go ahead and remove that as well from our circuit. Another thing to note, is that this circuit is written in the time domain. So while this is a phasor problem, when the source is DC, we cannot write it in the phasor domain because phasors must be sinusoids. And another important piece of information that we get from the problem is that it's in steady state. So we've drawn the circuit in steady state, meaning that the capacitors become open and the inductors become shorts. So we have pretty much a resistive circuit. And so I've gone ahead and defined the value we're looking for, which is I1. And so it also in the problem, it stated that this is the value that we're solving for. So I've gone ahead and drawn that here. And I've also drawn a voltage over here. So first we'll begin by doing KCL right here, which I've done right there. So we have the 10 amp source going in. We have I1 going out of the closed surface. And we have this current, which can be represented by Ohm's law as VA over 20 ohms, as these two are in series, as going out. So, and that all equals to 0. And so we also need another equation since there are two unknown variables. So we can do Ohm's law. So important thing to note with this is that this voltage is in parallel with this resistor over here. As you can see, you can kind of slide this negative sign down here. So we can do Ohm's law over this 10 ohm resistor, and we end up with this equation. And so solving for the two, we get this value, 6.67 amps. So it's important to note that this answer is already in the time domain. And with superposition problems, you need to keep track of what is in the time domain and what is in the phasor domain, because at the end we have to add all these I values up. So we can move on to the AC, to solving for the AC current source. Alright, so now we can begin solving for this AC current source. So I've gone ahead and drawn the circuit diagram. So as you can see, I've removed this source and this source, and I've converted this whole thing into the phasor domain. So these are impedances, and I've already gone ahead and converted these using this formula. And this is our AC source, and this is in our phasor notation. And so I've also defined I2, which is the value that we're looking for. An important thing to note with defining values on a phasor diagram is that they must be phasors themselves. They can't be in the time domain, because in an AC circuit, all the currents and voltages involved will be sinusoidal, since there's an AC source present. So To solve for this, I've gone ahead and done a KCL over here. All right, so this is our first KCL. And so this voltage is across this and this part of the circuit. So we've gone ahead and expressed this via Ohm's law. So this goes out of this closed surface. The current source expressed here goes into the closed surface, and this goes out of the closed surface. Next, we need another equation, so I've chosen an Ohm's law equation. And here, VC equals I2 multiplied by all that. So plugging all that into a calculator, I got this. And so, important to note that this is in the phasor domain, and we want our final value to be in the time domain. So we have to convert this back to the time domain, and we get this. So now we need to solve for our final source, which is our voltage source. Okay, so I've gone ahead and redrawn this. As before, this source is open circuited, and so this one. And as you can see here, everything is just in series, so we only really need one equation for this. So I've gone ahead and done that here. And so this is going around the loop this way. So we're going up to the negative, so right there. And then this is all one current that's flowing throughout the whole thing. I should probably label this. I3 will be flowing throughout this whole thing. And so we're just going ahead and use Ohm's law and just multiply all the impedances by the current, and we get this value. We get this value for I3. So once again, I have to convert this into the time domain, which I've done right here. As you can see, convert to time domain, all it is just putting the magnitude there and the amplitude there, and plugging the frequency back in. So now that we have all our three values for the current, we can go ahead and add them up. The final step in this problem is, now we have all of our currents. The final step in superposition is to sum up all the values. So one very important thing to note here is that all these values must be in the time domain before adding them up, or else we'll get the wrong answer. And so to add up all these, we simply just add them up. There's really no need to simplify, since simplifying trigonometric values equations are pretty difficult, so it's probably better to just leave it like this, and that's the final answer. Thank you.